of the third part of that tutorial. So now comes the interesting stuff. Attractors and their instabilities. So I have previously used this now, in a couple of cases already talked about something special about this intersection point. We call that a fixed point. So a fixed point is simply a point in which the right-hand side, the rate of change is 0. Fixed point because, I think I have a slide for that. Yeah, it's a fixed point because when x dot is 0, that means, if you have a solution where that's the case, that means that it's will not change. The future is just the same as the present. So that means it's a solution, and it's a constant solution, constant in time, right? And it's a solution of the dynamical system. So that's the point where that intersection occurs. Now, this is a solution where there is this negative slope, and I was already, always, this logic is always the same, that negative slope means if you're to the right, you have a negative rate, decrease. If you're to the left, have a positive rate, you increase. So you understand how you're attracted to this. And that's a fixed point of that nature we call an attractor. It's a fixed point attractor. It's a very trivial form of attractor. Mathematically, they are much more sophisticated kind of attractors. But in these lectures, we'll be only dealing with fixed point attractors. So this is true in the vicinity of the solution you're attracted. Could be, we'll see in a moment, there are cases when you move far enough from the attractor, you might not actually return. It's just in the vicinity, in ultimately some infinitesimal environment of the fixed point that you're attracted to. That notion of being attracted is what mathematicians actually call asymptotic stability, but everyone else calls it stability, and I also do that. And I'll explain in a moment that there is a subtle difference between asymptotic and regular stability. So asymptotic stability is really defined as the property of a fixed point that solutions that start nearby converge to the fixed point. Those who are mathematically skilled will recognize, starting nearby, that's a epsilon delta criterion. That is, there is an environment so that when you're inside that environment, your distance from the fixed point will go to 0 as time goes to infinity. That's asymptotic stability. That's a very fundamental concept we'll be using all the time, and you will see many uses of that. That has all kinds of implications if you have that. Now, what is actually mathematically stability, as contrasted to asymptotic stability, that is that nearby solutions stay nearby. They don't go off. They stay in the vicinity. I say that to those who know these sort of things a little bit, you might recognize that asymptotic stability is actually a concept that is not compatible with the Liouville theorem. I don't know who knows these sort of things. Physicists should. So Liouville theorem says that phase space volume stays constant, so you can't have that contraction. And that's true for conservative systems that conserve energy. All the physical systems, classical mechanics, electrodynamics, and so on, have these properties under some conditions. And therefore, they don't have attractive states. They only have stable states. So this classical question whether the planetary orbits are stable, that refers to stability in this sense. That is, will the planets be moving around the sun in a way that stays close to how they did it earlier, rather than fly off? Would one day Earth fly off into some other direction, everyone dying? That was a question that was a deep mathematical question solved by Poincaré, who proved that we can't actually decide, by the way. It's not very reassuring. It's a whole topic to just discuss that. And that's the concept of stability. And we only need that concept because it's the reverse of that is unstable. So if a fixed point is unstable, then that means it is not stable in this general sense. And that really means that there are nearby solutions. When you start in those, you don't stay close. That is, you diverge. Your distance grows beyond, so it does not stay within a bound. Again, this can be made more formal. And we already encountered the unstable solutions as these fixed points with a positive slope, which I'll come back to in a moment. right? So that's the only reason why you need to understand the difference between asymptotic stability and stability. So we will usually not really need this concept except as its inverse, that unstable, it's not staying close. So if a fixed point is unstable, it doesn't mean that it's not asymptotically stable. It just means it means more than that. It means it is really not even staying close. Okay. Most of the time, any nonlinear dynamical system can be looked at as a linear dynamical system close to the attractor. That becomes very intuitive. If you take this red dynamical system here, makes a zero crossing, and then you can think of the black curve as being the linearization of that red curve, which is asymptotic to the red curve at the fixed point. I drew this here by hand, but you can see it's a tangent that would cut through the red curve exactly at the fixed point. So those of you who know this sort of thing, it will be the linear term in the Taylor expansion of the corresponding nonlinear function. So you could perhaps intuitively see that for the fixed point, the behavior in this vicinity of the fixed point, the red curve and the blue curve will produce very similar behavior. We call these kind of nonlinearities non-essential. Physicists call these perturbative, which means that you can compute the functions, the solutions by solving the linear system and then solving some corrections, but they will be qualitatively very well described by the linear approximation. And that's actually, by the way, the reason why a lot of systems in the real world can be approximated as linear systems, because they're very often operated around fixed points. And due to the stable nature, the system will be near a fixed point most of the time. And then the linearization is valid. For instance, a lot of engineering is based on that notion. And sort of, I already, for some reason, I changed X to lambda here. Already said that you can decide the stability of a linear system by just looking at the slope of the dynamics as it goes through the fixed point. If that slope is negative, then the fixed point is asymptotically stable, is attractive. And I argued now several times about that. So that is a notion in a one-dimensional system, and I'll summarize in a moment what happens in a multi-dimensional system. Slope, how that generalizes. It's going to be about eigenvalues. So if you have a positive slope for a fixed point, that is an example of an unstable fixed point. I'll show you other kinds of unstable fixed point, but this clearly is an unstable fixed point. We also call that a repeller. Repeller is a special case where you're repelled in all directions. Here there are only two directions, left and right, but in multiple dimensions you can have many directions, and then the repeller is the radical case where it's unstable in every direction. Now, what if the slope is zero? If you like this extreme case in a linear dynamical system, just the rate of change is zero. There's no rate of change. You can think of that as what the position of a ball that's on a flat table. It's got to be really flat, and the ball's got to be maybe a little bit sticky for that. Then any point is a fixed point, right? We sometimes call that, in physics, we call this marginally stable. It is actually exactly a case where it's stable in this mathematical sense. It's not asymptotically stable. If you start in the neighborhood, you stay there, but you don't converge to the original fixed point. That's like a precarious situation. If you just give a little bit of inclination onto the table in gravity, then it will no longer be a fixed point. The ball will run off into the far, and we'll encounter this kind of situation exactly at instabilities. They will briefly go through a state like that. Now, this is about the linear system. We'll see in a moment what happens to the nonlinear system. And so the generalization to multiple, vector valued differential equations, multiple dimensions, uses concepts from linear algebra that those of you who are mathematically trained remember. So the generalization of linear system involves a matrix, right? You have the rate of change as a function of is linear to the state, and both are vectors. And so what connects these two is a matrix, a real matrix, and that matrix will have eigenvalues. And you can say the eigenvalues correspond to slope, if you wish. And you can say that the dynamical system, the fixed point will be stable if all the real parts of the eigenvalues are negative, asymptotically stable. And if there's only a single eigenvalue in which the real part is positive, it's actually unstable. So it's enough that in one direction you're repelled, and all others you can be attracted, but it still means that there are points arbitrarily close to the fixed point from which you diverge. So that's enough for instability. And generically, when you find that a fixed point changes from stable to unstable, it's usually one or two eigenvalues that change sign. The real part of them changes sign, and then you will see the divergence. If there is a real part that is exactly zero, then in that direction you have that marginally stable state, and that means really that it's not asymptotically stable anymore, and we'll see in a moment the consequences for a nonlinear system. Now, real part and imaginary part. So again, only to those who know roughly about linear algebra, these eigenvalues are complex numbers, and it's the real part that determines the stability. If you remember that the exponential, the solutions of linear differential equations are exponentials. If the exponential of a complex number has an exponential part that is the real part, and it has an oscillatory part, sine and cosine function, that's the imaginary part. So the imaginary part determines the frequency with which you either converge or diverge, and the real part determines the decay, exponential decay or exponential growth that you have around the fixed point. So you don't, this is just to connect the knowledge that they have. Those who don't know this kind of stuff don't really need that for the course. We will not really go very deep into these kind of more formal concepts. Now, nonlinear dynamic systems already hinted in this earlier slide that under many circumstances, the linearization captures the stability property. So if you have a nonlinear function and you can approximate it by a linear function around the fixed point, then the properties of that linearized system determine the properties also of the nonlinear system, with one notable exception. So this is a theorem. It's called the linear stability theorem, and says that the stability around a fixed point of a general nonlinear system is determined by its linearization, that in the sense that if the eigenvalues of the linearization are all negative, then you have a stable fixed point. If any of them has a positive real part, then you have an unstable fixed point. The only problem is if there's any real part that is exactly zero, then the linear system does not actually settle the question. Then it's not decided by the linear system whether the nonlinear system is stable or not. This is called a non-hyperbolic fixed point, but it doesn't really matter. That term doesn't matter. And I want to give you an intuition for that. So this would be the regular case of a dynamic. It's just a one-dimensional case, but this would correspond to having a negative real part. So the slope of the black line is the it corresponds to the real part of the eigenvalue in a one dimension, and the red curve is the nonlinear one. So that's what I had earlier. So you see the red curve predicts the stability of the black curve predicts the stability of the red curve. This would be the same for a positive eigenvalue. So the black predicts the instability of the red. And now you see why the slope equals zero doesn't determine stability. So this would be, for instance, let's start with this one here. This would be an example where you're going through zero and just become flat here. Maybe just this was done by hand, but it would be just let's say at the fixed point that your slope is zero. So your linearization has zero slope, but you might intuit that this is still a stable fixed point, because on the right you tend to have negative rate of change, and on the left positive rate of change, and that was responsible for this attraction picture. So this would be a stable fixed point, but its linearization isn't stable. While this has the same linearization, but that will be an unstable fixed point. And this similarly would be an unstable fixed point because it is unstable on one side. On this side you have a negative rate, so you would be escaping here to smaller values. And this is unstable on the plus side, because if you are on the right, you have positive rate of change and you escape in that direction. So you see that when you have an real part of an eigenvalue that is zero, you really have to look at the nonlinear system to understand the stability. Now, I get into a special case because that will be all critical when we do instabilities, because those actually involve a real part of an eigenvalue or a slope going through 0. And that's the next topic I want to briefly discuss. So, so bifurcations. Bifurcations are about families of dynamical systems, not about a single dynamical system, but about a family. We say family in the sense that you have a parameter that changes the dynamics. I mean, that function f, right? And what we want to look at here is parameters that change that function smoothly. That is, if you look at the function f, the dynamical function, there will be a continuous change. In fact, you can ask for the differentiable change of the dynamical function as a function of that parameter. And what we're interested in is to say, to which extent do the solutions of the dynamical systems also depend smoothly on the parameter? Or is it possible that sometimes a smooth change of the underlying dynamics can lead to an abrupt change of the solutions? And those will be the instabilities that will be important. This is a very general concept. It's the notion, sometimes called the notion of topological equivalence. This, you can think of the ensemble of all solutions of a dynamical system. This is an ensemble that is spanned by all the initial conditions. So the dynamical system can be viewed as the future of all initial conditions, sometimes called the flow. It's mathematically a mapping of the phase, the state space onto itself that depends on the parameter, which is time. And you could characterize the different flows, ensembles of solutions, relative to each other. You could say that they can be neighbors or not. So that's using certain topologies. You can think of it as a metric. You can define a distance. Mathematically, you need a little less than that. And the question that you're asking then is that as you are tuning a parameter, do the solutions of these different dynamical systems that are neighbors in the vector field, so where the equations are neighbors, are their solutions also neighbors? Or could it be that their solutions are qualitatively different? And there can be cases where they are qualitatively different. I'll show you examples like that. So let's take, I always take this example because we'll later see that that is something that happens in nervous systems. So I'm taking a case where something interesting happens here. So these are 3 values of a dynamical function as a function of a parameter. So let's say the lightly colored line and this darker and more saturated colored line would be 3 samples of a family of dynamical systems where you could continuously reshape the function from this shape to the top shape here. So intermediate values would be occurring. And I'm assuming here that there's an attractor that's common to all of them. That's actually irrelevant for our discussion. That will be the case in the neural dynamics. There will be always some other attractor you can go to. We don't consider these dynamical systems that mathematicians consider where the system can go off to infinity, minus or plus. So that's not something that happens. So we'll always have some other attractors to run to. But the interesting stuff happens here around this state, because here you see that there are members of this family where there are 2 fixed points. There's an attractor fixed point with a negative slope here, and there's a repeller fixed point with a positive slope there. And as I deform the dynamics by lifting it up, essentially, these 2 move toward each other. And you could imagine at some intermediate value, they will collide. And then as this lifts off, they disappear. There is no longer an attractor there. And that phenomenon around that point, that is a bifurcation. So it's a bifurcation is a qualitative change of the dynamics. It's a concretely, you can think of that as a change in the number, nature, or stability of fixed points as the dynamics changes smoothly. And I maybe can make intuitive here what that means. So let's say we're here in this limit case here, the with the two attractors and the repeller in between. We had that before. So this would be a case where any initial starting value of the variable around to the right of this repeller converges to this fixed point, right? So all the solutions here would be converging from left and right to this fixed point, while on the other side, they will be all converging to that attractor. In other words, around this repeller here, the solutions diverge. If you're a little bit to the right, you go here. If you're a little bit to the left, you go here. If you're sitting right in it, you would stay there forever. As the dynamic deforms, that boundary moves to a particular point, and then it abruptly disappears. So when you just increase the parameter from just touching to no longer touching, then here, just where that bifurcation occurs, there would have been this division where you either move to this side or to that side. As you go above, now every starting value converges to this. So there is no more reason why any one of those initial conditions would not converge here, because they all have a positive rate of change. So they all will move over there. And see, that's where a qualitative change will happen, where if you now have these ensemble of solutions, in one case, neighbors diverge, and just next to that parameter, the neighbors will have the same fate. So you could imagine these cannot be continuously deformed into each other. So they are topologically different. That is, solutions that are neighbors in one are not neighbors in the other description. And that's where it's no longer topologically equivalent. That's what we call an instability. So we will only use these concrete pictures of fixed points colliding and annihilating and so on. But the underlying mathematical theory is this idea that the ensemble of solutions, the flow, is no longer topologically equivalent, so it becomes quantitatively different. So let's look at that in a little more detail. We call this the tangent bifurcation. Right, at the simplest bifurcation codimension 0. I don't think I want to explain that here. So it's when an attractor and a repeller collide, and one way to look at that is to make a bifurcation plot. I call this local, and local means here, it has two senses here. One sense is that this occurs around this region in state space, right? So I didn't draw the critical case when it just touches here, that it just touches, it will be around that state, infinitesimal, around that state. And it's also local in parameter, because it would only happen for these dynamical curves, that are somewhere in between these two, that critical change happens. And as I move further, something else could happen. So it's local in that sense. And that is contrasted to global bifurcation. Sometimes you can have that at two distant locations that are distant from each other by a finite distance, some simultaneous change happens. And that's a big topic in the mathematical theory. And we're not concerned with that. We really look at local bifurcations in a sense. So here, for instance, this solution always stays. So there's nothing happening here. Yeah, I thought I had these bifurcations. Yeah, I'll come to that in a moment. Just wanted to say, you can experience this bifurcation in a system that you model in two directions. You can experience it, as I just suggested so far, that you're going from this state to the state without attractor, or you can go, from the state without an attractor to the state with an attractor. Right? These would be the two ways you could vary the parameter, and empirically that will make a difference. Either an attractor suddenly appears or an attractor suddenly disappears. That will be just a question of how you go through that. And mathematicians call one subcritical and the other supercritical, and all bifurcations you can look at in one direction or in the other direction. So this just summarizes that. Now, is a mathematical theorem that I will not, really formulate formally. Goes historically back to Hopf, but they're older. Mathematics is a whole landscape around that, and the theory says that these bifurcations, the qualitative change of the flow or the qualitative change of the number of attractors and their stability, those occur where an instability occurs. And that's why we're now using bifurcation and instability as the same term. But it's only because of that theorem that we can really say that. And instability meaning that that's where a real part of an eigenvalue goes through zero. So it goes through that case where the linearization no longer predicts the stability. That's an instability in the sense that if you think of the linearization characterizing how stable you are, how quickly do you return to the attractor, that will be where that takes longer and longer until it takes infinitely long. At the instability takes infinitely long. I'll show you some graphical illustration of that in a moment. So bifurcations and instability come together. They are sort of connected through that theory. So let's look at this, and this is the equation I put onto the exercise sheet that's uploaded, so you play with that and understand it. It's called the normal form of the tangent bifurcation. Normal form where it just means it's the simplest polynomial that has that bifurcation. So simplest in the sense, lowest number of terms. So that's not so important, but we sometimes refer to these normal forms. Mathematicians prove stuff about that. So it has this very simple form. It's x dot equals some constant minus x squared. That will be this sort of function. I'm asking you to plot that so you can actually copy here from the slides. But you better think through it yourself. And so you can see it's one version of the things I showed you. There is a zero crossing here with a negative slope. That will be an attractor. Zero crossing with a positive slope will be a repeller. And at this value, when alpha is 0, they just collide. They're just touching, and then it's gone. So for this dynamical system here, there's no fixed point. So any value of x, you have a negative slope, so you go to minus infinity. So this by itself would not be a great model. That would not use in our models, because then the activation would go to minus infinity. We need that other attractor that limits the decrease here. A good way to characterize bifurcations like that is to compute the fixed point, which is plotted here, as a function of that parameter. And if you compute that, you find it has the square root behavior. You have the positive slope, this one here, the positive fixed point is a plus square, and on the other side, it's a minus square. It only exists for positive alpha, while for negative constants, you're down here, there's no fixed point left. So you could see what happens is that a attractor, a stable fixed point, and a repeller collide and annihilate. That's the characterization of a tangent bifurcation. So I'm inviting you to study that a little bit on the exercise sheet, and this will give you a little bit better understanding. The result is shown here, but you have to do the computations for that. So for our work, so we really study this, we use these bifurcations, because what happens is that in the neurodynamics, we can say that these bifurcations occur in actual neural networks, and they sort of delineate different regimes from each other that have different functional meaning. It will be mostly the tangent bifurcation, sometimes will be the pitchfork. There's also the Hopf, but we will actually not use it in the lectures, but we use it in our work. The transcritical is not so important. It turns out that there is a classification of the kind of bifurcations that can occur. And I call these the simple ones, that is the ones for which no special accident needs to be the case, that are generic in some sense. And I don't go into the formal details of that. It has to do with the fact that that it's a question of how many eigenvalues cross the imaginary axis, so the real part becomes positive. And because eigenvalues of these dynamical systems always come in pairs called complex conjugate, it can be one eigenvalue or a pair of eigenvalues that share the same real part. So the tangent is what we just looked at. The transcritical is this sort of thing where you have a linear term here. So it is where there is a repeller here, an attractor here, and then you sort of pull here on this end, you pull that end down, it just touches here, and then you pull on the other end, pull it up. And what happens is that a stable state collides with an unstable state, and then we talk about the exchange of stability. So then this one becomes unstable and that one becomes stable. So it's just a mathematical oddity. We don't usually encounter that very much. It is maybe conceptually interesting in that you can see that if you're in a particular stable state, you can, you know, from the outside, if you just observe that, you will see this state, and then it goes on like that. And it looks like it's just going continuously. Experimentally, you might not even be able to see this, non-differentiable transition here. And but there is a loss of stability. That is, if you're close to this value, the slope is very flat, and you will have very slow relaxation, slow recovery from perturbation. So it is something that will have experimental consequences. So in order to observe bifurcations, it's not enough to always just look for jumps, something, a solution disappearing and the system jumping somewhere else. You can have these exotic cases. The pitchfork is more common. The pitchfork has formally this description: a linear and a nonlinear third order term. So the linear would be making here this straight attractor if the alpha is negative, and if the alpha is positive, the linear would have a positive slope. And the third order term is always the same. Third order, this is a third order function. It has a zero slope at 0. Take the derivative 3 times x squared. That will be 0 when x is 0. So it has a horizontal that's 0 here. And so if you superpose the linear to this nonlinear, then you get a straight, single zero crossing for negative alpha. But if you have this positive and this nonlinear negative, then you get this outer curve here. It's really around 0. The linear term dominates. The nonlinear term would become very small. And at large values, the nonlinear term dominates. So you follow the third order term. And that's why you have these conflicting solutions. So you see that in around 0, you have positive slopes, you have a repeller at 0, and then you have 2 attractors here on the outside. So the bifurcation diagram looks like a pitchfork. It is Heugabel, right? Like a fork. You have, this would be its grip that's stable, and then you have 2 attractors that emerge from that. In the middle is a repeller. So the repeller you will often not really observe experimentally, and what you will see is that an attractor splits into 2 attractors, or from the other side, 2 attractors collide into a single attractor. There's again the subcritical form, which I haven't plotted here, where you just, it's like letting time run backwards, so that this would be the attractor, and these would be all repellers or unstable states. And so the reverse pitchfork will look like an attractor, and then suddenly it disappears. The difference between the pitchfork and the tangent is that the pitchfork requires some kind of symmetry requirement. Those of you who listened to my summer semester lecture saw that in robots, obstacle avoidance, that sort of thing happens when 2 sensors approach an obstacle at the exact same rate. There's some symmetry between those. And so for symmetry reasons, sometimes you get that. While the tangent bifurcation doesn't really make any requirement about symmetry. I mean, this equation is symmetrical, but it could be, it doesn't depend on that. You can have other terms that break the symmetry, and you would still get the same phenomenology. So that's one that will occasionally show up in our work. The Hopf I mentioned only to make a point. The Hopf bifurcation is the one where an oscillation arises, and I want to make the point about higher dimensions, about vector fields. So if you have more than one variable, you can't actually plot x dot versus x, right? Because you have 4 things to keep track of: x1, x2, x1 dot, x2 dot. And so the good visualization is to just plot the vector of the rate of change. So a vector that has as first component x1, as second component x2, sorry, x1 dot and x2 dot. These are these vectors, and plot that in the same plane as the original state variables, so x2 and x1. So in a 2-dimensional plane, you plot 2-dimensional vectors that indicate the direction and rate of change. And so this is done here for a simple dynamic system. You can very easily see, you see the rate of change, you can see the attractor, right? It's where the arrows converge and the length of the arrows goes to 0. That's where the attractor is. Very intuitive. In fact, mathematically, you can find that the solutions would be paths in this plane to which these vectors are tangent. And that's actually, those of you know that sort of thing, you know that this is actually exactly the tangent vector. I mean, you take t as the parameter that describes the curves in this plane. So in this picture, you can say that the pitchfork, the Hopf bifurcation is when a two-dimensional dynamical system, so x1, x2, when a conjugate pair of eigenvalues crosses the x-axis, then you can have a transition from a fixed point into an oscillation. Now, for an oscillation, you really need two variables. That's very generally true. You know, if you think of that, the present determines the future. In an oscillation, you go through the same value in two directions, up and down, right? And so if you just characterize an oscillator by one variable, then the future isn't uniquely determined. In some cases, you go up from that same variable value, in some cases go down. And you need a second value that sort of disambiguates whether you're in the upstream, upflow, or you know, upswing or the downswing. And that will be that second variable. In physics, it's usually the second order. You have position and velocity, or velocity and acceleration and so on. But in general, it can be just some other variable. So a periodic solution in a two-dimensional space, is an oscillation. And so what happens here is that this would be one way to describe it using polar coordinates. You don't need to understand the math of it. It is actually also the pitchfork bifurcation, but now in the radius of the oscillation, and the phase of the oscillation is just constant. So again, this I'm putting out for those who have heard about these sort of things before, and so you make the connection. But if you have never heard about it, you don't really need to understand that for the rest of the lecture. The last point I want to make is what is useful. Why do I even talk about these sort of things? And that has to do with forward versus inverse modeling. So the way you learn about dynamical systems in math classes, calculus, and so on, is that you have an equation and you need to solve it. We call that forward dynamics, because you have the equation, the dynamics, and from that forward you compute the solutions. So here we'll do that by determining the fixed points and their stability, and analyze them in some way, or you can solve them by characterizing them through by analytical solutions or other means. Now, I'm pointing here to more advanced stuff you don't need to know. But if you're a modeler, if you want to model nervous systems or behavior, or design a robot, you often need to solve the inverse dynamics, which means that you know what kind of solution you want. You know that in experiment because you may have some experimental data, or you may know it as a design of a robot because you know what you want, how you want the robot to behave. Now you need to find the equation that has that solution as a solution. It has that time course as a solution. So that is really the problem that we're typically faced with when we model as theoreticians, when we derive the model. And so the idea is that what you can do is you can characterize the solutions by some quality, by attractor solutions and their stable states, for instance, and maybe by how those change when you change conditions. And then you can identify the class of dynamical systems that has the appropriate attractors and their change, which has the appropriate bifurcations. And then you can choose within that class of models some exemplar. So in some cases, we've actually used the normal forms, these polynomial solutions. In other cases, we don't. And you will learn some of those. We use what we call the Amari equation, which is a non-polynomial equation, but it's based on the same logic. We want to use the equation that contains the attractors and their instabilities, and that are sort of have some functional constraints, but there's no unique solution. There are multiple equations that can have solutions like that. And so that's why we actually need this kind of analysis, so that we know where we are. So when you in the space of equations, and when you do projects in our team, people make large architectures with a simulator. They design those and find parameter values, and what they're doing there is when you develop that architecture, they're writing down the equation, and the equation is constrained by constraints they have about the solutions. They know what kind of solutions they want under which conditions. And for us, that means concretely, they know which attractors and under which conditions they lose stability. That's how we design that. Okay, I know that this last part is certainly very advanced and rough. I mean, not easy to grasp if you're not in that realm, but I also want to give you perspective and show you what is behind it. It doesn't make sense that I water down what isn't actually so easy. So if you really want to become a modeler, you have to understand that background path. And so here I'm just hinting at that. It's not something that you will really need in your daily life. And with that, I close that tutorial.